So let's draw a system now. We have a system with a membrane in the middle that molecules can cross. So we have some molecules on the inside, and then we have some molecules on the outside. So we have some chemical potential on the outside, mu out. We have some chemical potential on the inside, mu in. We can define the change in moles of the inside, dN. Oops, this is not an I, this is in. Okay. The change in moles on the inside is thinking about how much is flowing from the inside to the out. Okay. And we can write the change on the outside in moles is how much is flowing outside into the membrane. Because we can't create or destroy mass, okay, the total number of moles has to stay the same. And so we can think of negative change in moles in is equal to the positive change in moles out. These two things have to be equal and opposite. Okay, whatever's flowing in is the opposite of what is flowing out, or vice versa. So if I want to write dG as equal to the chemical potential on the inside times the change in number of moles on the inside, plus the chemical potential on the outside, change in moles on the outside, okay? So if I wanted to look at the change in free energy of this entire system, I'd look at the inside and I'd add it up to what's going on the outside. I'm summing up my free energy changes, just like I can if I'm coupling two reactions, just sum the dGs. That's totally fine. Now I can substitute this piece in, so I can have this be negative dN in. And at equilibrium, if I set this equal to 0 at equilibrium, then I can pull my change in moles going in out. So I have chemical potential in minus chemical potential out times the change in moles flowing in is equal to 0. So this means the chemical potential on the inside and the chemical potential on the outside are the same at equilibrium. Or another way to say this is at equilibrium, the chemical potential of both regions will have reached the same thing, the same chemical potential. It'll be equal, however you want to think about it. For a spontaneous change, dG equal to chemical potential on the inside minus chemical potential on the outside times the change in moles. This has to be less than 0. By definition, dG is always going to be less than 0 for a spontaneous change. Okay. This is also delta mu. I think this is how you'll see it on your equation sheet. You might see it like this too. Delta mu dN. Ways to write that, ways to break it apart. If the chemical potential on the inside is greater than the chemical potential on the outside, what is the sign of this term? Right here. Okay. What's the sign of this term? If chemical potential on the inside is higher than the chemical potential on the outside, which way do things want to go? They want to go out, okay? Meaning that this term will be negative. Okay, so a way to think of this is we lose particles from the inside when chemical potential is higher in than out. or flow is from sort of higher number of molecules to lower. And so in sort of the opposite case, if the concentration on the inside, the chemical potential on the inside, although it's related to concentration, yes?
Because if you, for what we're doing here, if they're trying to get to the outside, like the
Yeah.
notation would make me think that the end would be positive because it's pointing towards the outside.
The change on the inside is going down. Does that make sense? The moles, number of moles in is decreasing when they flow out. So Dn would be a negative number. Yes? Like I'm asking for this term here, what's happening to the number of moles on the inside? And so the direction they're flowing is out, so the number on the inside is going down. Change would be negative from like sort of final state inside is a lower number than initial state inside, hopefully. Okay. And then alternatively, if I have this relationship, they're going to want to flow in. So I can think of the change of the number of moles on the inside between two states. This will be positive. Okay. Any questions about that? Yes.
When you have like the DN in, why is the arrow pointing out?
Ignore the arrows. I don't. It's the change on what's happening on the inside. So you could think of it, you could go ahead and just draw the arrows the other direction if you wanted to.
Okay.
Do you know what I mean? Like I just drew them as like, as I said it, they're going from inside to outside. This is like they're flowing out, or outside to inside, they're flowing in. It doesn't matter which way you write it, so long as when you think of N sub in as like the number of moles on the inside, and that when they flow out, you're only looking at the change on the inside, and it would go down versus the other way. Because you're right, DN, they flow in when it's the other difference in molecular potential, so chemical potential. So the arrows they were just for the story I was telling at that time. Don't maybe dwell on these. This is the change in how many are in the inside. This is change in the outside, and the direction they flow goes both ways.